Hello everybody, it's JT's Physics of Cycling video number 3. We'll actually introduce the 3 laws of motion donated to science by Sir Isaac Newton himself. Sir Isaac Newton was a very incredible person. He revolutionized physics. And for most of the physics that we currently do, outside of relativistic, quantum, and nuclear physics, Newton's laws apply to so many different fields. Engineering, all branches of engineering except for nuclear. And it's just absolutely incredible what this man contributed to modern science and mathematics. Sir Isaac Newton was also the co-founder of calculus, which is a very important branch of mathematics. But in the 1700s, Sir Isaac Newton came up with his 3 laws of motion, which govern us as cyclists. And I wanted to introduce those laws here and give an indication of what they mean. Newton's first law of physics states that a body in motion tends to stay in motion and a body at rest tends to stay at rest unless an outside force acts on it. Okay? This part right here, unless an outside force acts on it, is important. So just to take a minute and show you what that means, let's imagine, I don't know if you've ever skated or something on a farm pond as a kid, and there was a chunk of ice that got loose, and you're out here on this surface of ice, and you just came along and you gave this piece of ice a swift kick. Well, that piece of ice would just go and go and go forever because there's very little force of friction between the little piece of ice and the sheet of ice that it was gliding over. Another good example would be that of a hockey puck. There's almost no resistance or friction between a hockey puck and the surface of ice. So when that guy slaps that puck, it's going to go. It's going to keep going at that velocity with very little change. And then, of course, the ultimate example is, say, we fire a rocket into space. And once we get it into space, since there's no air in space, we can turn the engines off of that rocket. And it's not going to slow down. It's going to keep going. Actually, keep going forever. Because let's say here's a rocket ship out in space, and of course we have to blast off and get off the surface of the Earth, but once it's in space, we turn the rockets off. Here's the rocket without the engines on. It's going to keep moving, and it's going to keep moving forever. And that's what Newton's first law states, that a body in motion tends to stay in motion, and a body at rest tends to stay at rest unless we apply a force. Well, it's easy to understand that if we've got, a mass that's at rest, of course it's going to remain at rest unless we apply a force to it to get it going. Same thing there. So the reason I underlined the unless an outside force acts on it will come later here in just a minute. But these 3 laws are so important to us as cyclists. Law number 2 is where all of the math, in fact, libraries of math, are derived from this equation that force, which is a vector, is equal to a body's mass times an acceleration. So if you want to accelerate an object, in our case, say, a bicycle, and again, I apologize, I'm not a very good artist, say from 0 miles per hour to, you know, I don't know, 20 miles per hour, then you have to apply a force. And we all know, we all feel that force. We exert the force on our bicycles by applying a force to our pedals, and our drivetrain propels us forward. So we have to apply a force in order to our mass in order to accelerate ourselves to any speed other than 0. And then conversely, to decelerate a system, there has to be a force applied. So suppose we get up to 20 miles an hour and then we need to apply our brakes and come to a stop. Well, that force is coming from our brakes, heat. The energy of heat that we generate in our wheels and our brake pads is exactly or pretty close to the energy that we have stored up in ourselves, accelerating to that. So we can accelerate to 20 and then come to the stop by applying our brakes. Well, the energy that we used getting up to 20 miles an hour is the same amount of force that was applied to bring us to a stop. So the important thing about Newton's second law, and this is the big one, is that all of the math for almost everything in our real world comes from Newton's second law. And then, of course, Newton had the third law, which is probably the least used, and that is for law number 3. Every action generates an equal and opposite reaction. So if you apply a force to your pedal crank and your drivetrain, then you're going to get an action that's equal and opposite in reaction. And we don't use the third law very much, but it's still one of Newton's 3 laws of physics. Now let's talk about a couple of other things. Going back to Newton's second law, force is just mass and acceleration, but looking at it, acceleration is a change in velocity. Acceleration is a change in velocity divided by a change in time. So if at t0 you're at 0 miles an hour, and at t5 you're at 20 miles per hour, then your acceleration would be 20 divided by 5, or 4 miles per hour per second. That would be an acceleration. But there are also forces. Imagine, say, those kinds of forces where there is actual motion are considered dynamic forces, where motion is actually produced. But I remember working on a lot of problems. This is a cellular tower, okay? There's the cell tower, and this is, I don't know, 300 feet high. Now, I was involved in a lot of the engineering, the geotechnical engineering of a lot of cell towers back in the 90s, because that's when they were putting them all up. Now, let's imagine that we have, the engineers have to design these cell towers, in fact, everything, buildings, everything, billboards, highway signs, and everything. Even though that these things are specifically not in motion, in fact, we need them to be stationary, yet we know that there are still forces applied to them. Those forces are known as static. So there are 2 branches of physics derived out of the second law. Those that are static forces and those that are dynamic forces. And as cyclists, we deal with both of these. To finish my point, let's call this wind on a cellular tower. The cell tower itself has to be able to handle various wind loads. It has to be designed to handle that. The ground has to support it. The guide wires have to, etc. But this wind is a very significant force. O-R-C-E, force. So Newton's second law, even though it looks like motion is required for there to be a force, there are a such thing as static forces. In cycling, our states of motion, according to the second law, can vary, can go quickly from static to dynamic and back to static again. An example would be a cyclist, and I'm going to quit trying to draw the cyclist too much. Let's say going from 0 to 20 miles per hour. In the first few seconds of, say, a race, or or a ride, or a time trial, or whatever. Over this point, the first distance, the forces that are applied to the system are dynamic. Wherein there is actually a change in the energetic state of the object. But then, as we all know, since none of us can ride our bicycles consistently at 40, 50, 60 miles an hour, we will reach a point at which the system becomes static. Which isn't to say that there are no longer any forces acting on the object, but that the force applied to the object, okay, let's call this the force of the cyclist, becomes equal to the force of friction acting to resist any further acceleration of the object. At that point, the system becomes static and no further acceleration is possible. That all the energy to accelerate the system has become equal to the forces that are resisting the motion. But this is not to assume that there are no longer any forces applied to the system. And we all know that. If we go out here and if we hit 20, 23, 25 miles an hour and then we are no longer accelerating, we still feel the force is against us. So the force that we're applying is going in to the forces that are resisting, and the situation becomes static. And that's about it for this. For this particular video, Newton's three laws. I could say one more thing about the first law. A body in motion along a straight line. So there are other forces acting on us as cyclists. Looking down on, say, a map of a course, let's say a rider is going along this way and makes a big turn. As he makes this turn, there will be a force, a centrifugal force, because changing direction actually there needs to be an application of force, and that's because that the acceleration, say at this point, is changing directions to this point. And since acceleration and force are a vector, then there has to be a force acting on the object in order to change its direction. That's another important aspect of the first law and the second law. But I hope that's enough to educate you on my further videos, the three laws of Newton. and how they apply to us as cyclists is voluminous. I mean, there could be libraries of math that are derived out of these three laws of motion of Newton. And so we ride our bikes according to the laws of physics donated to us by Sir Isaac Newton in the 1700s. Thank you very much.